Time feels obvious. It moves forward. It carries us from past to present to future. It never pauses, never reverses, never negotiates. Our entire lives are structured around it. But when physicists began examining time closely, they discovered something deeply unsettling. Time may not work the way we think it does, and in some theories, it may not fundamentally exist at all. To understand why, we need to begin in 1905. That was the year Albert Einstein published his theory of special relativity. Before Einstein, scientists believed time was universal, a single cosmic clock ticking the same for everyone, everywhere. Einstein showed that this assumption was wrong. If two observers are moving at different speeds, they will not agree on how much time has passed. This is not a thought experiment. It has been measured. An astronaut traveling at extremely high speed will age more slowly than someone on Earth. A precise atomic clock placed on a fast aircraft will tick slightly slower than one left on the ground. Time stretches. The faster you move, the slower time moves for you relative to someone else. This phenomenon is known as time dilation. Already, our intuitive understanding of time begins to fracture. But Einstein did not stop there. In 1915, he extended his work into general relativity, and here, gravity enters the story. Massive objects do not simply attract each other. They bend spacetime itself. And when spacetime bends, time bends with it. The stronger the gravitational field, the slower time flows. This has also been confirmed experimentally. Clocks placed at higher altitudes tick slightly faster than clocks at sea level because they are experiencing weaker gravity. Even the GPS satellites orbiting Earth must account for time dilation due to both speed and gravity, or your phone's location would drift by miles each day. Near something extreme, like a black hole, the effect becomes dramatic. To a distant observer, a clock near the edge of a black hole appears to slow almost to a stop. From the perspective of the falling observer, however, time feels normal. Which time is real? The answer from physics is uncomfortable. They both are. There is no single universal time. Time depends on your frame of reference. Already, the idea of a shared cosmic present begins to dissolve. But the story becomes even stranger when we move from relativity into quantum physics. In the equations that attempt to unify gravity with quantum mechanics, something peculiar happens. Time disappears. Some of the most fundamental equations describing the universe do not require time as a variable. They describe relationships between states, not sequences, not flows, just correlations. In certain approaches to quantum gravity, such as the Wheeler-DeWitt equation, the universe is described in a way that does not include time at all. This suggests that what we experience as time may emerge from something deeper, not as a fundamental ingredient of reality, but as a byproduct of change. Physicist Carlo Rovelli has argued that time may be a perspectival phenomenon, something that appears real at our scale but dissolves when examined at the smallest levels. So why does time feel so persistent? One answer lies in entropy. The second law of thermodynamics states that entropy, often described as disorder, tends to increase. Ice melts, stars burn fuel, eggs break, but do not spontaneously reassemble. This increase in entropy provides what we call the arrow of time. It distinguishes past from future. But here's the twist. Most fundamental physical laws are time symmetric. They work the same whether time moves forward or backward. At the microscopic level, the equations do not care which direction time flows. It is entropy, a statistical phenomenon, that gives us the sense of direction, and our brains, forming memories of lower entropy states, construct the narrative of past leading into future. In this sense, the flow of time may not be built into the universe. It may be built into us. This leads to one of the most radical ideas in modern physics, the block universe. In this model, past, present, and future all exist equally. Spacetime is treated as a four-dimensional structure. Just as all points in space exist simultaneously, all moments in time may also exist simultaneously. Nothing is moving from past to future. Instead, every event is laid out in the geometry of spacetime. Your birth, this moment, events centuries from now, all part of the same structure. From this perspective, the feeling that time flows is an emergent feature of consciousness traveling along its world line, not something the universe itself is doing. So, is time an illusion? Not exactly. It is measurable. It affects aging, motion, and gravity. It shapes the cosmos. But it may not be fundamental. It may not be a river carrying reality forward. It may be part of the architecture of reality itself, or perhaps even more unsettling. Time may be what happens when consciousness encounters change, and the universe at its deepest level may simply be.